Hello and welcome back. Um, Chapter 6. You'll notice that there's a lot of notes on 6.1, and I don't do a video on 6.1. Um, and the video I'm going to do now is going to kind of cover 6.2 and 6.3 is what I'm planning on kind of together, because it's kind of basically the same idea, just kind of they apply it in two slightly different ways. 6.1's a lot of vocab. They talk about slope field. I hope in all my notes that I explain it sufficiently / combined with the book. You can always, search videos on Khan Academy or something if you need some extra explanation. But I can't do every single class. I'm doing like most of them on video. So, there's a lot of vocab. I explain that in my notes. The book explains it, right? Some of it we were talked about, like particular solutions where you figure out what the C is based on an initial condition they give you. Initial condition does not have to be a y value when x equals 0. Can be. And in some of these cases, you'll notice, before we talked about a plus C, we solved things when we had a plus C. Here you'll notice, like in 6.1, you'll notice sometimes it's a times C. That comes from essentially having a plus C after an integral, but then not already having that solved for y equals, having to go a step further to solve for y equals, and then you end up like raising both. Sorry, this seems like a lot spittier than the microphone position. Maybe it's a little weird. You always put a plus C when you do an indefinite integral, but then you always, so your solution to a differential equation should always, well, pretty much always look like y equals blah 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 x blah 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 blah. There could be a times C, there could be a plus C if it's a general solution. If it's a particular solution, obviously no C's. You should solve for the C once you plug in the given initial condition. There's going to be a couple where you can't really solve for y equals. It's just so gross at the end. You can't get all the way down to y equals. But the AP questions will actually take off points if you don't isolate y at the end. If that is a possibility. And I think for pretty much all the AP problems, that's going to be the case where you can get it all the way down. Slope field problems, like I said in my notes, those should end up being the easiest problems on the AP exam. Also in the notes I say no Euler's method. Just ignore all of page 392. Okay, 6.2. 6.2 and 6.3 I feel like are just kind of the same things. 6.2 and 6.3, well, both of them really have word problems. And they have some non-word problems. But maybe more heavier on the word problems in 6.2 than 6.3. Yeah, but even on the word problems, usually they still want you to use the words that they give you, write a differential equation, right? Differential equation means an equation that has not just x's and y's, but derivatives of y with respect to x, generally. To write the differential equation based on the context of the problem they give you, then solve the differential equation, and then usually get like a general solution with a C in there, and then they give you some kind of initial condition, plug in to find the C, and sometimes even from there, then they ask you to like find a Y given an X or that kind of thing. Yeah, and 6.3, they make it more explicit. They call 6.3 differential equations, separation of variables. But really 6.2, when you're deriving anything that you're doing in 6.2, you're also doing solving by separating variables. In fact, I don't like some of the notation they use in 6.2 to, oops, hopefully this is, okay. I don't like some of the notation they use in the beginning of 6.2 with the primes, that essentially they're kind of being hypocrites and they're not really separating their variables. I don't like that. I'll show you the way I do it. 6.2 in general, the differential equations involved in 6.2 are mostly based on the most like basic model of exponential growth or exponential decay, which you've all done in, I think we did it in pre-calc last year. If you're in finite, you've definitely done in finance stuff, like continuous compounding stuff. You might have even done it in other contexts there. So you've used, probably all of you have used the actual like general solution to the differential equation for growth and decay. You just haven't known why you can use that, where it came from. So we're going to briefly show how to derive that, but that's one thing that it's super easy to memorize. And then once you know it, most of 6.2 is using that basic equation, which is not really at that point even calculus, really. It's kind of like glorified pre-calc / finite math, to be completely honest. And then 6.3 is a more formal explanation of solving differential equations, and they call it separation of variables. Big picture here for differential equations. We're in calculus 1, we're only limited to solving what we call separable differential equations. That means separating anything with an x variable in it to one side, anything with a y variable in it to the right side, taking the integral of both sides, solving again for y. There's tons of calculus out there that is not limited to what we're calling separable differential equations. In fact, if you take calculus in college, you'll hopefully get to get the credit to get out of Calc 1, take Calc 2, take Calc 3, and then take a class called differential equations. And that is all about differential equations that are not separable. There's all kinds of like crazy rules and techniques for doing those differential equations. They're pretty bizarre. So yeah, we're just doing a very special, easier subset of differential equations. All right, so let's get started. 6.2. Whoa, okay, that's fun. I'm in the highlighter apparently. 6.2. Whatever, I'm not even gonna write the title. Whatever, okay. Differential equations, growth and decay. We're gonna start with example 1. Again, example 1, I feel like almost like they introduce how to solve separable differential equations, but then they essentially then just let you do a bunch of word problems with like the Kecht equation, if you know what I mean. And then they like revisit how to solve separable differential equations 6.3. That's why I'm just going to make this into one giant video, because it's all related. So example 1, and I don't love how they notate example 1. They essentially say to solve this, and they phrase it like this: y prime equals 2x over y, right? And you've seen this before. We've talked about those problems where you kind of like prove that you have a derivative, right? Like that dy dx equals 2x over y, and sometimes you're proving it by taking the derivative with respect to x at both sides, and then you end up having to do, right, the implicit differentiation thing, where like if you take the ddx of a y, or like say the ddx of like y squared, you have 2y times dy dx. Well, you take the ddx of x squared, it's just 2x. Anyways, hopefully you remember that. But even in that case, we don't like using y primes. We want to use dy dx. Okay, so immediately I would tell you, and the book does not do this, rewrite using dy dx. Okay, so rewrite y prime as dy dx, right? Just always do that. The book does that, I think, in 6.3, but it's like they're hypocrites. They don't do it in 6.2. Dy over dx. That's going to help you out with the whole thing, the whole idea of separable differential equations. Okay. And then, and again, they don't even explain the whole separable idea in this problem. I just don't love the way the textbook handles this. Again, the idea of separable differential equations means you want to get all the x variables on one side, get all the y variables on the other side, and to know which side to get them on, right? Because like in this case, it's like, well, do I move all the x's to the left side and all the y's to the right side, or vice versa? Well, right here, if I moved the x's to the left side, that means I'd have to divide both sides by x. And on the left side, I would have, right, and then for the y, I'd have to divide the left side by and the right side by dy. And I'd have 1 over quantity x dx equals 2 over quantity y dy. We don't want dx and dy in the denominator. We've never integrated something with a dy or a dx in the denominator. That's silly. We would never do that. So you would put them on, you would put the x's and put the y's on whatever side makes the dx or the dy be in the numerator. Okay. So this is kind of like the first step if you need to deal with that. And then like the second would be move all x's to one side and all y's to the other side such that dx and dy are in the numerators. Okay, so like here, our dy is going to have to stay on the left side because it's already in the numerator. Okay, so in this case, we're going to have to multiply both sides by y, right? And also multiply both sides by dx. Now the 2, it could be on either side. You can either make it a 1/2 on the left side or a 2 on the right side. My suggestion would be to move any constants over to favor the x side, because you're going to want to eventually isolate the y. So it just makes it a little bit more annoying to keep constants by the y, right? So I recommend putting constant multiples on the x side because we're going to want to isolate the y eventually. Okay, so this means that y goes to the left side. Great. Now we need the x to go to the right side. So we also need to multiply that side by dx. So that goes away, and multiply this side by dx. So on this side we have y dy equals 2x dx, right? It's usually not going to look this simple, but it is what it is. Then the third step is going to be, great, now you have all the y's on one side, all the x's on the other side. take the integral of both sides. Step 3, take the integral of both sides. Antiderivative, you know what I mean. And side note, super important, right? When you do that, you would normally put plus c's on both sides. I can show you why you actually need to put a plus c on one side. Put a plus c on one side. I would highly recommend the x side. I'll show you why you don't need them on both sides. Okay, so integrate this. In fact, when I go to integrate the right side, I'm just going to go ahead and integrate, just like pull the 2 out, right? We know we can do that. The integral of y dy, antiderivative is y squared over 2. And so normally, right, normally we would say that this is plus c. I'm going to call it c sub 1 because we're going to have 2 different c's. Equals 2x squared over 2 plus another c, if I call that c2, all right? So these are presumably different c's, different constants. I guess it's possible they're the same, but we don't know that. Likely different. Okay, but like, if you're gonna have 2 different unknown constants, well, how about we just do this essentially, and how about we just say that we subtract C1, right? So that this side is going to be like a plus C2 minus C1, which then down here I'm just kind of working ahead. Well, okay, if we have an unknown constant that's equal to C2 minus C1, why would we overcomplicate things and have an unknown constant that is made up of the difference in 2 other unknown constants, right? That's kind of silly. So what we do, right, we just, let me see if I can kind of, hello, let's do like a red thingy. Oops, don't want it there, right? So we just take this out, we just, oh, that's not what I wanted. We just say, nah, we don't need that. We don't need that. We don't need that. We don't need to call it this thing. Don't need that, right? So all we're actually going to do, instead of doing all that, hopefully you can understand where I'm going with this. We're just going to do a plus c on the right side, right? We're going to skip all that stuff. We don't need it. We're just going to say, okay, I understand. We would normally have 2 unknown constants. Since we have 2 unknown constants, we're combining them to one side, and we're just going to call that new unknown constant plus c. All right. Okay. Now these 2's cancel. So we have y squared over 2 equals x squared plus c. Now, we could say, right, if you try to solve this for y, it's just not pretty. You could try to solve it for y first by multiplying this by 2. And again, if you try to multiply this by 2, this is where, people are going to be bothered. But it is what it is, I know. Ready? If we do this to both sides and say y squared equals 2x squared plus, and you would normally write 2c, you wouldn't be wrong, but we don't really care what the original unknown is, right? We're not ready to even like plug in anything yet. So if we need to modify an unknown into a different unknown, it's still going to be an unknown. Like, sure, we could call it c sub 2 or something, but since we don't really care, because we're never going to use the original unknown, we're just going to keep calling this C. I know it's going to bother you or some people, but this is one time you kind of have to just kind of let it go. It's a new unknown. We're calling 2C. We're just renaming it C because we can, right? I know it's usually we're like very precise about that stuff, but that's what everyone does. Now, you could keep going and take the square root of both sides. If you did the square root of both sides, you would have to do a plus or minus, remember here. And then I guess in this case, the C would have to be under the square root because you can't split up the square root over addition. That's kind of icky. So in this case, I would allow either of these, so that one or that one. Usually it's going to work out where you can solve for y equals and not have like a icky plus minus square root thing. It is what it is. Okay, yeah, the bottom of the page explains what I explained about the whole like C2, C3, C3 minus C2, they call it C1, you know, that kind of thing. Okay, moving on, page 398. So page 398. So we're deriving a classic exponential growth and decay. That's not a D, that's supposed to be like an and sign, decay model. So you've all used it. But you probably haven't derived it yet because you didn't know calculus. All right. So the book says, in many applications, the rate of change of a variable y, okay, so when the rate of change of some variable, so some quantity y is proportional to the rate of change. So when the rate of change of the variable y is proportional to the value of y, right, and y is a function of time, meaning y is changing over time. Right, when this set of circumstances is true. All right, this sounds kind of like strange, but the rate of change of y is proportional to the value of y. For example, this is like for finite people or like continuously compounding interest. The more money you have, the faster your interest compounds. Similar to like generic exponential growth, right? Like when you have an exponential growth model of like y equals 2 to the power of x. Similar to that. But in this case, it's like continuous compounding where the base is e and not 2. You often have, so some of the word problems we're going to have in here have to do with radioactive decay. So sometimes the rate of change is a negative, so some value is decreasing, right? For example, like example 3 talks about like the half-life of plutonium isotope 239, right? And so like the rate of change of how much plutonium you have is actually proportional to how much plutonium you have at that moment, meaning like the less plutonium you have, the slower it's going to decay, right? It actually decays the fastest right away. It decays slower over that time. Or something like example 4, population growth, right? Like they're talking about like fruit flies or something, right? This is like the same as population growth for humans or animals or anything, right? The more humans you have, the faster the rate of change of humans is going to be, right? Like if you just have like a small town of like 20 people, 10 married couples or something, and then you got to wait for them to like grow up and have kids, and then like those people grow up and have kids or whatever, that rate of change, depending on how many kids they have, whatever. But assuming that their population is going to grow over time, it's going to grow, but it's going to grow slower. What if you, okay, even for the same city, it's the population is growing, but then what about 10 years, I don't know, 100 years later when you have 200 years later when you have like 1,000 people, I don't know. The rate of change then is actually going to be faster because now you have like, 500, potentially like 500 couples, having babies, like bam, 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 bam. They're like, the rate of change of that population is growing faster and faster and faster. Like think about like an exponential curve, like right? Um, like example 5 talks about declining sales due to advertising, right? Like the more people who know that a product exists, the faster your sales are going to grow. Example 6 talks about Newton's law of cooling. So we even talked about something similar in maybe physics 2. If you think back to, well, we didn't do a calculus example, but we did do something about conductive heating. Anyways, hopefully you can vaguely understand why this is important. Okay, so let's interpret these words, right? So this is what is going to be important. Interpreting the words into math symbols, which is going to be a differential equation, and then using the techniques we know about solving separable differential equations into whatchamacallit, into a general solution. Okay, so the rate of change of variable y. The rate of, I meant to make this a different color. The rate of change of the variable y. Rate of change, and is varying over time. Okay, so that means dy dt. Again, we're going back to things changing over time, so make sure you write dt. Okay, so that is, right, is in math is the same as equals, okay, is proportional to. Now this one's a little bit trickier. Is proportional to means if you have one thing and you multiply it by a constant, you get the other thing, right? If, I don't know, how many kids I have or how many slices of pizza I need is proportional to how many kids I have, and each kid wants 2 slices of pizza, right? Well, then if I have 3 kids, 3 times 2, 6 slices of pizza. If I had 10 kids, 10 times 2 would be 20 slices of pizza. Luckily, I'm only having 3 kids, so I don't need 20 slices of pizza or 10 little mouths to feed. But anyways, is proportional to. So is proportional to, this is going to be a constant multiplier here, and this is a constant. Proportional to is like k times, right? A constant times the value of y, right? The value of y is just y. So the rate of change of the variable y means equals proportional to k times value of y, right? Again, that means like if y is higher, that means dy dt is higher. Like if you have more people, your population growth is faster. Okay. So that's how you write your differential equation for that particular case, if that is true. If that is true, how you would solve it, so deriving the solution. So deriving the solution. And you should know how to do this. Now here we don't have x and y, we have x and t, right? So we're going to put all our y's in one place, and the dy needs to be in the numerator. So I'm going to, let's see, I'm going to multiply this by 1 over y. 1 over y. So that goes away. And then the t I need over here, so times dt times dt. Okay, so I'm going to have, so that goes away. So I'm going to have 1 over y dy equals k times dt. Okay, so I separated. K is a constant. It could go anywhere. We try to keep the constants away from the y's to make things easier. Okay, separate the variables, integrate both sides. I'm keeping the constant outside the integral. Okay, be careful. The antiderivative 1 over blop should be ln absolute value of blop. ln absolute value blop. Normally be plus c, but again, we're going to add the plus c on the right side. K, all right, antiderivative of 1 is just, well, normally we'd say x, but it's whatever the variable is. Here we have t, so it's not going to be an x, it's going to be a t, right? So kt plus c, right? There's our unknown constant. And this y, now like in our case, you'll notice the book doesn't put an absolute value. So now they derive this, or prove it, whatever. In the middle of page 398, they don't put an absolute value on their y. Notice y, so if y is always is always a positive number or a 0, then you don't have to put that. So this is just equal to normal y if our y is greater than or equal to 0. And the things that we're going to be talking about are things like amount of plutonium left, number of people, dollars of sales, amount of energy, that kind of stuff. It's pretty much always going to be positive, possibly 0, so not negative. So that's why they usually drop the absolute value thing. Okay, so we're going to rewrite ln y equals kt plus c. Again, we want to solve for y though. We don't want to just leave it like this. So to solve this for y, we're going to raise e to the power of both sides. E to the power of this whole side. This is super important. You cannot raise e to the power of just the kt and then have an extra plus c. That's not how this works. E to the power of ln y is just y. Okay, e to the power of kt plus c. This is where, if I was in person, we would probably have more of a discussion or whatever. But remember, if you have something like, remember back when you had x, let me see, I don't know, x to the 2 times x to the 3. Okay, what was that equal to? Hopefully you're saying x to the 5, x to the 2 plus 3, right? It was x to the 5th. All right, so it's like x times x times x times x times x. Bunch of x's, that's 5x's, x to the 5th. Okay, now we're working backwards. Now we know we have a base to a power where the exponents are added. We can kind of like distribute the base as long as it's then multiplied. So we're coming over here. Okay, so this is equal to e to the kt times e to the c. You see that? Hopefully I made you trust me with this little side note. Okay, now again, we're going to do that little thing where we, since our c is unknown, if we need to modify our unknown to be a different unknown, we just keep calling it c. So we're going to just call this e to the c. If c is an unknown, we're going to call e to the c unknown. So we're going to rename as c. okay? And we're going to put that c in the front. So this is going to be y equals c times e to the, move this, kt, kect. Sometimes people use different variables, but ce to the power of kt. Yeah. So this is where we get c times stuff from, not a plus c, but a c times or something times c, is because it was a plus c when we had the ln y equals, but then we raised e to the power both sides to isolate y, so that's why we ended up with a c being multiplied instead of added. So here's our whole little thingamabob, right? This is deriving this solution of exponential growth or decay. And so you're allowed to just use this y equals c times e to the power of kt for these word problems, which at that point, it really is not a calculus problem anymore. So hopefully it's easy, question mark. Let's see. Let's see what else I want to talk to you about. Okay. Let's see, if we just derive this, I guess we can. Did I mean to, real quick, I'm going to look this up. What did I mean to do with this? Yeah, okay, that's all I meant to do. I'm going to mostly leave it to you to do most of the other examples. To read the examples, take notes on them, etc. Example 2 is just a very bare bones type of example with no real life application. Note that they're assuming that y is changing with respect to time. A lot of these, right, you'll notice that there are, let's see, can I change this? Back to that, okay. Notice that there's two new, that's not really ratchet. Okay. Move this. Notice that there's two unknowns here, right? So there's two unknowns. Two unknowns. C and K in these models. So basically, when you're doing these word problems, they're going to have to give you enough information so that you can solve for not just C, but you also have to solve for K. So they can't just give you one data point, you know, not X comma Y here, it'd be T comma Y. They can't just give you one data point T comma Y because then you could only know either C or K. But oftentimes they will give you, implicitly give you the value of Y when T equals 0. So if you're given the value of Y, so if you have an initial, so if you know, given the Y u at T equals 0, right? That's the data point 0, comma, I don't know, let's call it Y1. Well, I guess let's call it Y0, sub-0, whatever. Why not? Whatever. Get it? Why not? Well, that was pretty good, actually. If you're given that, notice when you plug it in here, right, when you plug it in here, you're going to get y naught equals c e to the k 0. E to the 0, e to the k times 0, which is e to the 0, e to the 0 equals what? Equals 1. So that means, therefore, Therefore, y to the 0 equals c, right? So if you're given the initial value, the initial amount of y, that's actually c, right? So this c here is the initial y value when t equals 0. The k is a little bit more nuanced than that. The big thing to know about k is it has to do with like the rate of growth, but it's not obvious. You're going to just have to plug in the values of y comma. So once you know c, and if they give you another value of y at a different value of t that's not 0, then you can plug that in and solve for k. Generally speaking, when k is less than 0, we have exponential decay, right? When k is greater than 0, we have exponential growth. Okay. So like, for example, you look at example 3. Oh, it tells you that 10 grams of the plutonium isotope, blah, 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 is released. How long will it take the 10 grams to decay to 1 gram? Well, they tell you that it starts with 10 grams, so that immediately tells you C. And this one's kind of tricky. They would have to tell you the half-life of plutonium. So I would not give you a problem and expect you to know the half-life of plutonium. I would have to tell you what the half-life of plutonium is. What is half-life? Half-life means half-life, like if you're plotting time, and this is like y, this is like the amount of a substance exponentially decaying. And this is the time, right? Whatever the value starts at, let's say it starts up here, half of that initial amount. So if this is, move away. Yep, close. You know what I mean. Okay, half that initial amount. So if this is, well, let's call all this y. Let's call this y naught, and let's call this y naught over 2, right? So the decay thing is going to look kind of like that kind of deal. So when the amount of whatever it is gets down to half of its value, the time it takes to get to half of its amount, this is called the half-life. You've probably heard of the video game or whatever, right? The half-life is the time taken to reach half of its initial value, right? It takes to decay to half its original value. Okay, so when you know the half-life, you can plug in, remember the half-life is in time, so that's the time when the amount of plutonium is half what it originally was. It originally was 10, so when it's 5, you notice they plug that in, they solve for K. Once you do that, then you get the exact model, right? So we're looking on 399 toward the bottom of the page. In red it says half-life model. So once you solve for K, and you are pretty much given C. So now you have the model. So now you have the particular solution. Now you go back and look at the question. The question said, how long will it take for the 10 grams to decay to 1 gram? So you know when your y you want to be 1, what is your t? You plug in 1 for y, you already know c and k, you don't know t, right? Hopefully you remember how to solve equations like that from 10th grade and probably also from pre-calc, right? You have to divide both sides by 10, take the ln of both sides, and then you'd have the ln of 1/10 equals that really long gross. Decimal number times t, divide both sides by that gross decimal number, then there's your approximation. Notice when you're doing these problems, especially the k values, are going to be like really long decimal answers. If you can use the store button on your calculator, reteach each other if you've forgotten to store the exact value of k, that's perfect. You will be allowed to use your calculator on anything that has like gross numbers like this. So I do think that all or at least part of your next test, quiz, whatever thing, you're allowed to use your calculator because of icky stuff like this. And yeah, so remember, so for k values especially, or any intermediate values, keep full decimal stuff. You know, if you round that k to 0.0000288, your answer is going to be off by a good amount. Do not round your k values. Please store them as the exact amount. At the very least, write down all the numbers you see on the screen and use that number, okay? Everything else is very similar. Something like example 4 is a little bit trickier because they don't give you the initial amount, but they do give you 2 data points. They tell you there's 100 flies after 2 days and 300 flies after 4 days. So instead of like immediately knowing your C, you're actually going to have to do a little like mini system of equations substitution-y thing to get your C. So notice like you just plug in those 2 data points, like 2, 100 and 4, 300. And like here, they just, let's see, what do they do? Yeah, they plug in, oh, let's see, C, oh yeah, they just solve for C in one of those 2 equations and then sub in for the other equation, use that to solve for K. Then you can go back substitute, solve for C, you get the particular equation, and then just remember they're then going to ask you a separate equation. They're not just going to ask you for the particular equation. They're then going to ask you to use your particular equation to model, right, approximately how many flies were in this case, original population. Okay, so make sure you answer the exact question they're asking for. Useful precision around your final answer to 3 decimal places. Okay, I say in my notes, ignore example 6. Okay, and then we're going to go to 6.3 real quick. Example in 6.3, I'm going to do examples 1 and 2, and that's pretty much it. I also think, I seem to remember in 6.2 maybe, there's one answer that's like a little bit like strange. Even when you look at the solution, you're like, what in the world are they doing? I think it's like 6.2 homework problem. I don't know, I'm gonna say 7 or 9. I don't remember. Anyways, I feel like at some point, maybe it's in the 6.3 one, they have you plug back in for the value of y. Actually, I'm probably thinking of another section. Whatever. You probably think I'm losing my mind. That's fine. I think I'm thinking of something earlier in the year. Okay, 6.3. But again, it's 6.3, 6.2. It's kind of the same idea. Yeah, so for 6.2, almost that whole thing, you're using just that like Keck equation. Oh, I don't know if I have this written down. Hopefully this will help you. If I don't actually have it written down, I think I have it written down in your weekly schedule. But for the 6.2 homework, if I still have number 42 assigned, notice the change that they make a mistake there in the word problem for number 42 on your homework for 6.2. It says a piece of ancient charcoal contains only 15% as much of the radioactive carbon as a piece of modern charcoal. They should have switched those words, ancient and modern. That doesn't make sense. If you have radioactive carbon, you would lose carbon over time. You would not gain carbon over time. So the modern charcoal would only have 15% as much as the ancient charcoal. That's just wrong. Okay, 6.3. Again, it's called differential equations, separation of variables. I'm not going to write that. It's the same stuff. So, example 1. Find the general solution of this thing. And they actually already have it written in terms of dy dx, so you don't even have to rewrite y prime as dy dx. Xy. Okay, so again, first step is get all the x's on one side, all the y's on the other side, where your dy has to be in the numerator, dx has to be in the numerator. So it looks like our y's must be on the left side. Okay, so gonna have to multiply both sides by 1 over y, because dy is in the numerator on the left side. So there goes the y. And the dx is going to have to be on the right side, so that means the left side is going to have to get multiplied by, let's see, 1 over x squared plus 4 dx. Right, so that this, and same with this left side, 1 over x squared plus 4 dx. So we're balancing everything. So that the dx goes away. This thing gets canceled. All right, so what do we have now? We have 1 over y dy equals x over x squared plus 4 dx. Okay, integrate both sides. Okay, we've had this same integral before. Antiderivative of 1 over y is ln absolute value of y equals integral of this thing. Hopefully you're not thinking arctan. Well, you might think it, but then hopefully you go, nah. Why is it not arctan? Because if it were arctan, our u would be x, right? Because it'd be u squared over u squared plus a squared. If our u was x, our u prime would be 1. But we have an x up top. Can't be that. So it actually has to be where this whole thing is our u. So then our u prime, whatever. I'm going to be lazy. U prime is 2x, so we need a 2x here. So that needs a 2. That needs a 1/2. Hopefully you're getting the hang of integrals by now so that you can kind of do them fairly quickly like this. Our outside function, I'm just going to write that as an f of x. What's being done to this? It's just 1 over that thing. So the antiderivative of that thing is going to be ln of that thing. Hello. Please let me write. Okay. So here we have our 1/2 comes down from here. 1/2. 2x, remember, that's a u prime, it goes away. Ln absolute value x squared plus 4 absolute value plus c, right? But we still need to isolate y. Oof. Babe, staying up with mommy. It is ridiculously late. Okay, so let me see if I can move this because that's getting in our way. Isolate y. Great. Okay. In fact, I'll just do red, whatever. So we e to the power of that whole side e to the power of this whole side, the entire side. Okay. In fact, probably before I even do that, yeah, I'm probably gonna do that, aren't I? Let me see what they're doing. Yep, they do that. All right, hold on, hold your horses. Before I do that, I mean, I have this 1/2 out front. I have this 1/2, and I have a log. Remember what you can do with the log thing? You can rewrite it as a power. The 1/2 power is the same as square root. Okay, and the stuff under the square root better be positive. So some of these things with the absolute value, we kind of just like hand wave it away and go, yeah, hopefully it's positive. Especially because we're going to raise e to the power of, and then like e to the power of has to be positive. Anyways, just kind of go with it. So ln absolute value y equals ln, and now we're just going to make this this thing to the 1/2, which is the square root of this thing. See, you picking up what I'm throwing down? I hope. Yeah. So now we're going to do e to the whole side of that. E to the whole side. Again, the whole side. Please include the plus c in that. If you do these without including the plus c, you're going to be wrong every time. You can't take e to the power of only part of one side. You got to do it to the entire side. And so, again, with like a little hand waving with the absolute value, like, meh, whatever. Pretty much goes away-ish. Just kind of pretend. Now, remember with this is going to be, right, you like kind of split this up. So it's like e to the ln root x squared plus 4 times e to the power of c, right? So here, the e and the ln essentially like kind of go away, and this is just like brought down, more or less. And the e to the power of c, right, we're going to rewrite this as just a normal c, right? Because if c is a constant, e to the c is also a constant. It's still an unknown constant. So this is going to be y equals c square root. Okay. So I'm just reading the book. So the book does, okay. The book does keep the absolute value y, and then makes the right side plus or minus e to the power c, but then again, they kind of have some weird hand waving too, where like c is equal to plus or minus e to the power of c sub 1, and it's fine. Writing it like this is fine. Okay. Yeah, technically, I guess you could do like a plus or minus thing. I don't usually see problems where they have a plus minus in their answer. Okay, let's do example 2. This is a general solution where you just have an unknown c. Okay, I'll zoom out if you want to pause it on the whole thing. All right, that's all of example 1. Example 2. Okay. Example 2, and then I think that's all I'm doing. Given the initial condition y of 0 equals 1, find the particular solution of this big ol' thing. Hold on to your hats. I think I can make that a little smaller. Okay. They have this written weird. They usually have the dy dx together, but whatever, it is what it is. They have it separated already. It's kind of strange. xy dx plus e to the negative x squared. times, so come on, times y squared minus 1 dy equals 0. Whew. All right, so we separate the x's and the y's. Since they're both in the numerator, it doesn't matter which side they go to, but you just have to pick a side. I don't know, how about x's stay on this side? Okay, fine. So let's subtract this whole thing. I'm not going to write it. That's a long thing. You know what I mean. Subtract that whole thing. So we have x, y, dx equals negative e to the negative e to the x, y squared minus 1 dy. We can keep the y's on this side. All right, so what we need to do, just sprinkle in some red so it doesn't, all the black doesn't blend together. All right, we got some y's on this side, but this e needs to go over here. Now, let's see. Are you all going to be offended if e to the negative x squared is actually already in the denominator? So, and I'm going to take this negative with me because again, I want to get everything as much away from the y's as possible. What would you guys say, right? So this is in here. What would you say if I multiplied this by negative e to the positive e to the x? Do you see how that would cancel? Because this is actually negative 1 over e to the x squared. See that? I'm about to erase this, but okay, so that means I'm going to also multiply this by negative e to the x squared over here. So that that whole thing cancels that whole thing. Okay, I'm going to erase that. And then, so now our x's are on the left side except our y here. We need to divide by this y. Divide by a y here. Okay. So what do I have? I have, and I'm going to write the x, I'm just going to write this x in front of this. So negative x e to the x squared dx equals, and I'm going to go ahead and, so we're not trying to confuse ourselves, I can just distribute that y. So it's just going to be y minus, I'm just going to go ahead and write it as y to the negative 1, because I know I'm about to integrate this thing. Well, actually, though, I guess it's not going to be a power rule thing, is it? It's going to end up being an ln thing, so whatever, I'll write as 1 over y. Okay, I take the integral both sides. Okay, hopefully you'll follow me. All right, the right side's going to be fairly straightforward. Right, this right side's just going to be y squared over 2 minus ln absolute value of y. I would only put a plus c on the right side, but I'm going to put a plus c with the x's. Over here, looks like this is going to need to be my u. U is x squared. And so my du dx is 2x. Right? So I need a 2x, so I have a 2 here. So I'm going to have, I need a 1/2 outside. I'm going to move that over. And then I'm going to have a 1/2 out there to fix that. Again, this is my u prime, it goes away. Okay, so negative 1/2 has to come down from there. My outside function is e to the blob, right? X is e to the blob. Antiderivative e to the blob is e to the blob. So negative 1/2 e to the, what is the blop? The blop is x squared. I got to put my plus c here. Right, now this is definitely a case where they ain't no isolating y. You got a y squared and you got an ln y. So here we can't. It's just not algebraically feasible. I don't know, maybe some crazy PhD person can do it. I can't. But remember our whole goal is to find the particular solution given we know the point 0, 1. Okay, so plug in the point 0, 1. Okay, to find C. Okay, so -1/2 e to the 0 squared plus c equals 1 squared over 2 minus ln 1. ln 1, e to what equals 1 is 0. E to the 0 squared, e to the 0 is 1. So if I add 1/2 here, add 1/2, c equals 1. So my particular solution becomes, and you'll notice the book probably is going to multiply. Yeah, they don't like leaving fractions here. The book likes at the end multiplying everything by 2, but notice they multiplied everything by 2 before they found C. Oh, no, they didn't. Just kidding. They did exactly what I did. So they're going to plug in C equals 1, but then they're going to multiply everything by 2 just to make it look better. Bet they're fancy and they do y squared too. Yep, they do that. Predictable. So what I mean is, all right, so C equals 1. So this, no, that's, okay. C is 1. That's C. All right, so this, and I'm going to write the y's first. So y squared over 2. No, it's not plus. Sorry, I'm losing my mind. Minus ln absolute value of y equals -1/2 e to the x squared plus 1. But then they just, for kind of style points, they just kind of multiply everything by 2. So then they have y squared minus 2 ln absolute value of y equals, let me distribute this. So -2 times 1/2 is just 1 e to the x squared plus 2. And then they do this little trickery thing here too, and they bring that up there. And then if you're squaring absolute value of y, then of course it's the same thing as y squared. So then they have y squared minus ln y squared equals, and they probably write it like this, don't they? Because of course they would. Oh, they write it weird. They get a 2 on one side. Doesn't matter. Whatever. This is fine. Okay. Example 3, you can look at yourself. Notice it says has a slope of y over x squared at any point. That just means dy dx equals y over x squared. Do not do anything with the homogeneous differential equations. Don't read it. Don't look at it. Close your eyes. 407 and 408 pages in the book. You don't need to do that. Don't look at it. Read the other examples I tell you to read. I try to explain what they mean by orthogonal trajectories in my notes. For example, 8, orthogonal just means perpendicular. It doesn't come up a lot, but essentially they give you a family of curves, y equals c over x. They want you to find the orthogonal trajectory of curves that are orthogonal to that graph, which means perpendicular, right? Remember, perpendicular lines have negative reciprocal slopes. So that means you need to find the formula for the derivative of the tangent lines to the original. So you need to find dy dx. And then you take the negative, which they show you is negative y over x. This is page 410, example 8, which is negative y over x. And then you take the negative reciprocal of that. Boom. So now your new differential equation for the orthogonal trajectories is positive x over y. Then you solve that differential equation. Boom. Get that. Example 9. It's a good example. It's a pretty good example. I would look pretty heavily at that. 10 is pretty good. Again, kind of examples 9 and 10 are good examples of where 6.3 is a little different than 6.2. 6.2, you pretty much use that Kecht equation for like everything. You don't have to usually derive your own differential equations. For examples 9 and 10, those are showing how they're explaining to you a situation. They're explaining a differential equation in words. And then you have to write out the differential equation in words. Then you have to solve the general differential equation with a k and a c usually. Then they've kind of either explicitly or implicitly given you information that will allow you to solve for the c and the k. And then after that, finally, they want you to use that to like predict a value, usually like a y value at like a later point in time or something. So that's a good problem. Again, the book does a pretty good job of explaining it though. Right, so for example, in example 9, the second sentence says the rate at which the population hears about the product, right? The number of people who have heard about the product is the y. So the rate of y, so dy dt, is proportional to, so equals k times the number of people who are not yet aware of the product. Now, that's kind of tricky. The number of people who are aware of the product is equal to y. And they say there's 1 million potential customers. So if we take y to be millions, so we don't have to write out 6 zeros after our people. So the people who have not heard of it would be 1 minus y, like 1 million people minus how many people have heard of it tells you how many people have not heard of it. So that they show you how they write that differential equation, do the separable differential equation thing, integrate, get the general equation, plug in the knowns they've given you to solve for c and k. And then once you've found c and k, then they want you to predict how many you've heard of the product after 2 years. So plug in t equals 2, and so on and so forth. Okay. Good luck. I know I'm having you have a little bit more responsibility of reading and understanding a little bit more of this with a little bit less handholding from me than I did in chapter 5, but hopefully you can do it. Help each other. Read the solutions and the solution manuals. When in doubt, if you need some extra videos, Khan Academy and that kind of stuff can help you out. I would say these differential equations are important, but maybe a little less important than some of the stuff from chapter 5. Well, yeah, I'd say definitely less important than the stuff from chapter 5. Hopefully I will be back in time to teach you 7.1 and 7.2. And let's see, yep, 7.1, 7.2, and nope, we don't have to do 7.3, just 7.1, 7.2, and then hopefully we'll have our last little test quiz, whatever, on that stuff right before spring break. Come back and like right after spring break, do like a day on L'Hopital's rule, which combines limits and derivatives. It's easy, don't worry, it literally takes 1 day. Then you'll do your tutorials. Ooh, good luck. I'm a judge, so yeah. I also have a personal motive for wanting you to write some coherent and interesting and meaningful papers in addition to just for your own sake. And trying to do your best and not just give up at the end of the year and succumb to senioritis. And yeah, so hopefully I'll see you for those, and then we'll review in Q4. All right. Again, hope you're all doing well, and hopefully I'll see you soon. God bless.